In the previous video, I talked about secure design principles. The point I tried to make is that designing security into a system right from the beginning is both more effective and less expensive. The way we do that is often through defense in depth. We identify possible attacks along the way, and we implement defenses for those attacks as we build the systems. That creates a defensible system from the beginning, rather than having to worry about adding controls or countermeasures onto its system after it's been built and maybe even taken into production. We discussed a few of those principles. We discussed least privilege, we discussed separations of duties, and we discussed isolation. In this video, I'll discuss a few more. And then in the next video, we'll talk about security frameworks that give specific guidance as to how to use countermeasures in systems design. Encapsulation is a technique that we know from software engineering. It is the technique where we try to bundle objects, operations with the data on which they operate into objects or object classes. And the idea there is that we can shield the inner workings of these functions from the way in which they are used. And that is a good principle. It's a principle we also use in cybersecurity. We often use it when we're dealing with legacy systems, where we know that we have a system that needs to be protected but was not built with those protections in mind. What we can try to do is wrap that system into a layer of additional protections, which doesn't affect the system itself, but it does affect the way in which we use the system and in which we deploy it. The key there is that when we use encapsulation as often almost a last resort of protection, is that we define a very clearly defined interface, similar to what we did with the firewall and the intrusion detection system. We describe a way into the system and we describe a way out of the system, and we try to shield the system from all other possible interactions. And by defining that narrowly defined concept of an interface and defining how that interface can be used, we can add protections to an existing system. We wrap it into a security bubble. But what is important to realize is that we haven't actually secured the system itself. We've just secured the environment in which the system functions. But if that's the only option we have, then that's what we'll do. It's really a continuation of the isolation principle that we talked about in the previous video. If we want to use encapsulation and isolation, we need to have a mechanism or a technique to do that. And again, borrowing from the realm of computer programming, we can use modularization. What we're doing is separating the functionality of a system in self-contained units of work, where again, we define interfaces between those units, but we try to shield the inner workings of each of those units of functionality from the rest of the world. That has benefits from a software engineering perspective, because it allows for easier source code maintenance. It allows for us to operate on one unit without affecting the rest of the system, for example. But because each of those units provides more clearly defined functions, it also becomes more clearly understood how we need to secure each of those units. And so there's a benefit right there. If we do it well, and if we group functionality with like functionality, we might be able to reuse software. Software reuse is a double-edged sword. On the one hand, by reusing software, we might be reintroducing vulnerabilities that exist in the code base that we are reusing, and by using the same vulnerable code in multiple places, we create different attack vectors. But it also goes the other direction. It means that if we secure software in one location and we use it in others, then all of the other locations are also more secure. And the idea of using appropriate modularization is that we can secure software in one place, and then hopefully the trickle-down effect will cause all the other systems that use that software that we just created to become also more secure. By breaking down the software into smaller modules, we get yet another benefit. People are not necessarily great at understanding very large-scale systems with lots of complex interactions. But if we can break down this system into smaller subunits, we can start reasoning about those subunits and we can start seeing a bigger picture. That approach is often called abstraction. And abstraction helps us to understand the interactions within a system better. And a system that we understand better is a system that we can defend better. One of the key tenets that we'll see often come back is that complexity is the enemy of security. Or the other way around, simplicity benefits security. And because of that, we often use modularization techniques when we design software. As an example of how things can work maybe not so well, some time ago a vulnerability was discovered in an encryption library that was widely used by other systems. It was called OpenSSL. And because it was so widely in use, when that vulnerability in OpenSSL itself was discovered, hundreds of thousands of other systems were found to be vulnerable as well. And this led to a Heartbleed vulnerability, which was one of those early software vulnerabilities that actually had their own logo, that were branded, and that were trying to communicate out to the security community like there's a real problem here. This kind of supply chain issue is a major one. By fixing OpenSSL, and then the next stage, of course, is recognizing where OpenSSL was used and fixing those systems as well, we were able to resolve the problem mostly. But having an effect like that, especially these, what you sometimes might call, deep libraries that are far removed from end-user functionality, it's not always clear immediately what those dependencies are. And software reuse, as I mentioned before, is a double-edged sword. In this case, it led to a rapid proliferation of vulnerabilities across systems, but it also meant that by fixing the root cause of the vulnerability in one location, all the other systems could be patched relatively easily. It's still a process that we need to go through. It's a process that we'll talk about later in this class as well, but it is something to be wary of. Mentioned before, simple is good. So there's this design principle that goes with that, simplicity of design. The more easier I can make it to use a system, the more likely the system is going to be used. Likewise, the more easy I can make it for a system to be secured, the more secure the system most likely will be. Complexity is the enemy of security. Why? It's very easy to make mistakes when you don't necessarily know how all the moving parts of a system interact. It's also hard to predict how a system is going to behave once it's going to be put together from all those different components. And lastly, it becomes very expensive to manage, the overhead that comes with a complex system. A while ago, we had an issue in a software library called NTP. That was the Network Time Protocol. NTP is old software, well, old in the terms of the internet. The first version of the NTP software was written in the 1980s. It's a small piece of software that's present in almost all computers that can synchronize that computer's clock against an authoritative time source somewhere out on the internet. All PCs do it, all Macs do it. They go back to time servers provided by Microsoft or by Apple or by Ubuntu Linux distribution. There's time servers everywhere. Stratum 0, GPS time synchronization in many cases, and then as you start removing from the authoritative source, your numbers go up. But because the internet is a network, and it is a network that consists of many smaller networks, the speed of the network is going to have a massive impact on this. If I'm going to synchronize my clock against a network time source across the network, but the network itself introduces a delay, I need to compensate for that delay in my time synchronization efforts. And NTP was a very complex protocol, and still is a very complex protocol that does that. It's able to compensate for network latency and data loss and get your computer synchronized at millisecond level. For most applications, a second more or less isn't too important, but there are also many applications where microseconds are important. NTP can be used for those. Now, why is that important? Because the software was written in the 1980s, it's very complex software, and it worked. And so no one really touched it anymore after that. They were afraid. It was so complex that people are afraid that by making a change in one location, it could have an unpredictable outcome down the road. And as a result, when a vulnerability was discovered in NTP, there were some discussions that that vulnerability might actually have been there for maybe 20 plus years. And that's a long time for a vulnerability to exist without being noticed. Part of the reason was that it was very complex code. The other problem was now we have to fix it in very complex code, which takes a lot more effort, and as a result it's more expensive and takes longer than if the code would have been very simple. Security through obscurity does not work. Sometimes we'll see that deliberate efforts are being made to make a system less transparent. And the idea is, well, if no one knows how it works, it has to be more secure. It's not the case. Never try to improve your security by making things less transparent. It just does not work. In the long run, it will always come back to cause a problem. With simplicity of design comes minimization. Very simple. If you don't need it, remove it. Because if you don't have it, it can't break. So minimize everything. Turn systems and services off that you don't need or that you don't use. If you don't need to be running on your computer with full administrative privileges, get rid of administrative privileges, drop them. Lower the amount of data that you're collecting. If you don't need it, don't collect it. That way you don't have to protect it. Purge data when you can. And minimize functions shared by different users. All of that, doing the least amount of work possible with the least amount of code and the least amount of data, makes a system a lot more defensible. So the minimization principle gives birth to the idea that you should never assume that your system is running in a trusted environment. The system should protect itself. It should not rely on the environment to protect it. Now, unfortunately, if we start designing security into our systems and we start, for example, making things harder for attackers, it also means that we might be making things harder for legitimate users. And as a result, we always have to strike that balance between security and usability. If we are not careful, we're putting up so many constraints on the usage of a system that the usability of the system significantly suffers. And in the end, a system that is not usable is a system that is not available, and a system that's not available is a system that is not secure. So this is a strange paradox that by adding more security controls, we might actually end up with a system that is less secure overall. The other part that you have to be careful with is if you start putting barriers in front of users who need to use that system to do their job. It means that you always have to keep in mind that a system is built to do a job, and it should help people do their job. If you start putting constraints into place that make people less effective at doing their job, they will find a way to bypass those constraints. And that means, and it's lore in many different places, that part of the onboarding of a new employee is explaining to that employee how to bypass many of the security controls that are built into a system so that they can do their job. The IT team and the security team is often oblivious or chooses to be oblivious to those things. But the reality is that we may on paper have a secure system, but that in practice people bypass these controls all the time because of some form of a weakness or a vulnerability. And if a regular user can figure out how to bypass a system's security controls, an attacker can too. And at that point what you're defending is a system that seems to be secure but really isn't. So when implementing these security controls that affect usability, always be very careful to make sure that you're not putting barriers in someone's way that will lead to them trying to bypass those barriers in the first place. Another feature that sits on that borderline between security and usability is the rule of least astonishment. The rule of least astonishment basically says a system should behave the way you expect it to behave. It should also not do strange things. For example, if I hit a button marked save, it should actually save my work. It shouldn't delete it. It means also that a system that acts predictably is a system that's probably more secure. A clear example of that is listed here. So for example, I am a Mac user. On the Mac user, Command Q is typically a shortcut for quitting the program that I'm using. But I often run virtual machines on my computer. And that means that when I'm in a virtual machine and I want to quit the applications that are running in the virtual machine, I expect to be able to hit Command Q in that virtual machine. Unfortunately, the way that some systems are built is Command Q doesn't kill the running virtual machine. It actually stops the entire virtual machine process, which means that all of my virtual machines might stop working from that point. And that's a surprise. The same thing that we might see in Chrome web browsers, where I might have a shortcut that closes Windows. Chrome now has the opportunity to say, hey, do you want me to warn you if closing the last window will actually close the browser altogether? That's in line with that least astonishment rule. The system should behave the way you expect it, and if you're going to do something to a user that they didn't expect, you should probably warn them that you are about to do this. So back to the previous example, if you're going to quit from a program that did not save its work, maybe the program should say, hey, you didn't save your changes yet. Do you sure you want to do this? Very simple control to build into the software, but potentially very large benefits. With that comes the idea of secure defaults. The easiest way to think about this is a user will click an OK button if it is there. Or maybe hit enter, and whatever the default choice is, that's what they'll accept. Many people do that when they have security pop-up boxes. So maybe in terms of user interface design, and the pop-up says, "Ooh, you're about to give, very dangerous access to an attacker. Do you want to continue? Yes or no?" With yes being the default choice, that wouldn't be such a smart option. Maybe what we would say is, hey, you're about to do something really dangerous. Do you want to abort? Yes or no? With yes then being the safe choice and the default choice, where you almost have to make conscious effort to shoot yourself in the foot. Those are the secure defaults. And even though that's not a technical control, it is a control where we are starting to look at user behavior rather than at the system itself. But in many cases, and we'll see this coming back many times throughout this class and other classes as well, we can come very close to designing secure systems as long as no people are involved in the use of that systems. As soon as we start introducing people, it becomes a whole lot harder. So when it comes to giving these people a choice, we need to make sure that those choices, the default choices at least, are clear and are secure. Google understands this in their Google Chrome application. If you go to a website that presents an invalid certificate, you'll get the screen that's shown behind me on the screen. And basically what it says is the default choice is to not continue, and you actually have to put in some effort in order to be able to continue. You have to go through the advanced options, and then you have to find the button that is disguised as the link that isn't the button at all, but still gives you the capability to continue. This is a clear example of how we do want to do these things. That's the end of this video. I introduced some security principles, secure design principles, I should say, both principles that attack the technical side of securing as well as principles that apply to the human side of securing. How to put all of these principles together is often discussed in frameworks, and those frameworks are the discussion topic of the next video.